Okay, class, so this video is going to be on Stokes Theorem, which is really long, but it doesn't say a whole lot even though it's so long. So we let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve, C. Sometimes they refer to it like this. I don't know what to say there. It's just sort of a symbol that they use sometimes. With positive orientation. F is a vector field whose components have continuous partial derivatives on an open region in 3 space containing S. Then, here's the theorem. Okay, so the line integral over that boundary curve, over the vector field of that boundary curve, is the same as the surface integral of the curl of F with respect to S. Okay, and the deal with this theorem is this is a two-way theorem. So if they ask you to do a line integral, you're not. You're going to do the surface integral of the curl. If they ask you to do the surface integral of the curl, you're not. You're going to do the line integral over the boundary curve. So this is a two-way theorem. So let me do an example here. So we're going to evaluate the line integral over the vector field F. I should tell you what F is. So F is minus y squared x z squared. Okay, and let's see. We need the curve. So C is the intersection of the plane y plus z equals 2, and we're going to have the cylinder. X squared plus y squared equals 1. Okay, and usually they put more here. Usually they say C is positively oriented, which once again, so this is our picture up here. So you can see you've got some kind of surface and you've got a boundary curve. Okay, and in this case, if I were to draw things, we'd have a cylinder and it's going up and meeting a slanted plane. So this is my curve C. So what we're going to do is we're going to make that plane the surface. Okay? Alright, so if we're going to make that plane the surface, we need to parameterize the plane. We need to find the curl of the vector field, and then we can do our business. Okay? So curl of F, because remember, if they're asking us to do this one, we're going to do that one. Okay? So the curl of the vector field okay, so this is the partial with respect to x, partial with respect to y, partial with respect to z, and then down here we put minus y squared, x, and then z squared. Okay, and this is really straightforward. So the I component is going to be the derivative with respect to y of z squared, which is 0, minus the derivative with respect to z of x, which is 0. First component 0, yay. Second component, the j component, would be partial with respect to z of negative y squared, which is 0, and the partial with respect to x of z squared, which is 0. And then last one, k component, the partial with respect to x of x is 1. And the partial with respect to y of minus y squared is minus 2y. So the only component we get out of this is going to be the k component, which is nice. Alright, parameterized surface. We're going to parameterize an x and y because it's a plane. So this would be x, y, and then if I solve this for z, I'm going to get z equals 2 minus y. So 2 minus y. And then Rx is going to be 1, 0, 0. R sub y is going to be 0, 1, negative 1. And we know that the cross product of this is supposed to be minus f sub x minus f sub y comma 1. And so Rx crossed with Ry is then going to be, should be using vector arrows, shouldn't I? Okay, so Rx crossed with Ry should just be 0, 1, 1. Okay, so if we dot these two guys, that's going to be the integrand of the region. So this is going to be the double integral over our region D, which D is the plane. Okay, so the plane bounded by the cylinder. Okay, so the cylinder is going to give us our bounds, and so we're going to integrate 1 minus 2y with respect to area. Okay, and since this is a cylinder, we're going to convert that to polar. So it's a standard cylinder. So 0 to 2 pi, 0 to 1, and then 1 minus 2 r sine theta, and then r is the integrating factor, dr d theta. And this is very easily integrated. So when we integrate this, what are we going to get? Well, we're going to get essentially the integral from 0 to 2 pi of r squared over 2. I'm try to make that legible. R squared over 2 minus, not plus. Minus doesn't matter. It's going to be 2r cubed over 3. Because remember, this is going to be r, and that's going to be 2r squared sine theta d theta. Why doesn't that matter? Because integral from 0 to 2 pi of sine is going to be 0. So we're just going to get, and this is evaluated from 0 to 1. So that's going to be a half. We're going to multiply it by 2 pi, so our answer is going to be pi. Okay. Let me do one more example. So this time we'll go the other way. So in this example, they ask us to evaluate the surface integral of the curl. So I guess I should tell you evaluate, which I think we're not going to evaluate it. We're just going to, actually we might, we'll see. So the line integral over the curl, over the surface of the curl, and I need to tell you what f is. F is going to be x z y z x y. Okay, and what's the surface? S is the part of the sphere above the xy plane and bounded, oh, I should tell you the sphere. Okay, oops, forgot that. X squared plus y squared plus z squared equals, what are we going to get? 4. Okay, so that's my sphere, and it's bounded by the cylinder. X squared plus y squared equals 1. And once again, we should say that the surface has positive or upward orientation. Look, if they ask you, if they say negative orientation, it's no big deal. Just you're gonna do a line integral, just change the sign. That's all. So, all right. So back to the theorem again. So they're asking us to do this, so we're going to do this. Okay. So when they ask us to do the surface integral of the curl, we're not. We're going to do the line integral. Okay. So just so we know what this looks like. So you have a sphere, the radius 2, and a cylinder of radius 1, and it goes up and intersects that sphere, and that's going to be my curve up there. So we need to figure out how to parameterize that curve. And look, it's pretty simple. It's a circle because it's bounded by the cylinder, and it's at a certain height. So we've got to figure out what that height is. And that's no problem because we know x squared plus y squared equals 1, and we substitute that into the sphere. So 1 plus z squared equals 4. That means z squared is going to be 3. So z is going to be root 3. Okay, so now we know the height of the cylinder. So r of t would be cos t sine t root 3, and that's our cylinder. Okay, or that's our circle. All right, let's see. What do we need to do? We need to do f of r of t and r prime. So what is f of r of t? Okay, that's xz, so that's going to be root 3 cos t. And then yz, so that's going to be root 3 sine t. And then xy, which is cos t sine t. Okay. R prime. So what's that equal to? That's minus sine t cos t and 0. Sorry. I could say root 3, but it's not 0. And then look, when we dot these two things, so f of r of t dotted with r prime of t, because that's what you have to do for a line integral over a vector field. So that's going to be negative root 3 sine t cos t plus root 3 cos t sine t plus 0, and those cancel each other out, right? So this is a line integral over c of 0, which is 0. Well, I guess I could say from a to b. It doesn't really matter what a and b are, but that would be 0. And probably in this case, I didn't check it, but maybe the vector field back up here, maybe it was conservative, and we know if it's conservative, the curl's 0. That is something you can check, but in general that's not going to happen. It just so happened in this particular example. So we got something that was really easy to find a line integral of. All right. I do want to just say one last thing. Sometimes sometimes the surface is like a slanted plane, and you have to, or you're trying to find the line integral with the cylinder intersecting a plane. And so, like, let's say x squared plus y squared equals 1 intersected with z equals 2 minus y. That was our last sort of problem. We didn't have to do the parameterization of that. But let's say in the future, if they asked you to do the surface integral of the curl of that vector field over that, you would then do the line integral, and you would need to know the equation of that parameterization. And this is pretty easy. The x and y parts are going to stay the same. It's the z part that you sort of need. So r of t would be cos t sine t, and then see your y is sine, and your plane is 2 minus y, so you just do 2 minus sine t. And that would be your parameterization for like a slanted plane if you needed it. Okay, that wraps it up for Stokes theorem. Next time.